Swayam Prabha. Digital India. Educated India.
Okay, so I have here two tubes. What is this? Plastic, PVC tube. What is this? Copper. Copper. This is copper, no? This is plastic PVC. Now I have some small piece. Okay, can you, somebody else come, please come. I'll do it here so that it will not fall to the ground. I don't know how many of you can see from the distance. That's the problem. If you go to the back bench. Okay, now mind. Now what I'm going to drop this small, see this, can you see that? It's a small metal piece I'm going to drop and he's going to catch it. Can you catch it at the bottom? Put both your hands. Like that. So I'm going to drop, put it down so that I can see what is coming out of it. Thank you. I didn't get your name. Anand. So I'm dropping it. All of you see what is happening. It's coming out. Take it out. Try once more. Don't do any experiment once and say, Huracan, run on the road, man. You have to keep repeatedly and it should, same results should come. Comes out. Good. Now I take the copper tube. Coming out. Once more. Coming out. Why?
Gravity.
Gravity. Don't say there is a hole in it. In some place they said, sir, there is a hole. Then I said, yeah, well, it comes even without the hole. Right? Okay. Now what I do? I take another metal. Now I take the PVC tube, please. I'm dropping through that. Coming out.
Yes, sir.
You have to get into IPL. Yeah. Good. It's coming out. Thank you. Go ahead. I want to do it. I don't want it. You know why? I'll put it and keep talking to you. And then go slowly and catch it. 100 rupees ticket. This is magic man. See here. Gravity switched off by a small micro switch in my shoe. You believe that, huh? So can you tell me what is happening? Somebody said already what it is. Magnet. Neodymium, boron, iron, alloy magnet. Very powerful magnet. It will be about 2000 Gauss. Okay? Very, very high. So what? Will magnet attract PVC tube? No. Will magnet attract copper? What is this? Anybody can tell? Yes or no? No. Yes, yes, no. So how do you classify materials on the basis of magnetic properties? Fantastic. Great. Paramagnetic. Ferrimagnetic. See, you have to see all the classification. Of course, there are some of them are out of syllabus. I told you, no, you would not have had occasion, but it doesn't matter. But there are several classifications. Very interesting molecules are there that will be able to, professor will be able to help you on that. Now, what is happening here? So, what is this? Is it? So, there is nothing like a non-magnetic substance in the world. Earlier, LKG, UKG, you can talk about magnetic, non-magnetic. It's all right. But when you graduate little higher than what you should say, you cannot escape magnetism anywhere. Okay? So, which magnetism is prevalent everywhere? Diamagnetic. As long as an electron going around a nucleus, there is diamagnetism. Electron will produce a current. That current will produce a magnetic field. So it is always there. But that diamagnetism is negative. It will oppose. Paramagnetism will attract. This is weakly paramagnetic. Copper. So it will attract but very less. But then why it is coming slow? That should be a different concept altogether. And that concept is by our great, phenomenal scientist who is an inspiration. Can you connect, sir? I will show. Who is an inspiration to every young people. What is his name? Equivalent to Newton or even better, some people say. Not Tesla is one, of course. Faraday. Michael Faraday. Michael Faraday, he started as a bookbinder. For all of you, I tell you, more than the physics or science, you should read about the scientist. Then only you see they also have two eyes on one nose. Otherwise, what we do? We put like Mahatma Gandhi in a big pedestal, nobody need to follow him, right? That's a normal thing, no? So if you see the life history, the biography of great scientists, you get motivated that such a simple man can do phenomenal things like Tesla, like Michael Faraday, bookbinder, with a difference. Whenever science books comes for binding, he will take 4 days. He will take it home, read, and then only return. He was so passionate. He came into contact with Sir Humphrey Davy. He's a great scientist, Davy's lamp, Cavendish laboratory. So he said, sir, let me come and help you in your lab, cleaning things up, ready, because I'm passionate. That guy somehow took fancy to this guy. He said, from tomorrow come to my lab. After a few years, who became the head of the Cavendish laboratory, Cambridge? Michael Faraday. These days it won't happen here. In those days it happened. But that is still phenomenal thing, the fellow. You can imagine. And you know what he did? Every week he will have a public lecture in Cambridge. Anybody can walk in. And what he will show, you will have a big thing. We have in physics lecture theatre, big podium where we will put all the things that he tried throughout the week. Whichever were successful, he will show. This I did, it was fantastic. This I did, it didn't work. Maybe I'll show you next time when it is working. Like that, he will share his knowledge. So at that time, he took a big coil. This is a coil. Solenoid we call it. I have put a tape on top. Inside the tape, what do you have? Copper. Winding. Okay? And the two copper ends are connected to a, what is this? Galvanometer. What is the difference between ammeter and a galvanometer? Galvanometer will measure very fine small currents. That is the grandfather of ammeter. You convert the galvanometer later to ammeter, voltmeter and all those things. Galvanometer is a basic conceptual device, DR Sunwall meter. Okay. So now what happens? You can see it is deliberately meant to be at the center, the pointer. Now what happens? I have got on the stickmer. So now I am going to drop it, this same magnet here, which I showed you some time back. I am going to drop it, see what happens to the, can you see what happens? What happened? Now I will invert, see what happens. It goes on the opposite direction, right? That is all. Super. He showed same experiment to his audience. One MP was sitting there in the front bench. He said, oh, Michael, you want to call this something great? That's what he said. Then, you know what Faraday said? My dear gentlemen, in 5 years' time, you will be charging people, taxing them. That is electricity. 95% of the electricity that we all enjoy, even today, is because of this guy. Same thing. Where is it coming from? Kalpakam. Hydraulic project, thermal project, all of them are what? Ultimately what they do? Water falls, I put 2 wires, I get electricity. Is that true? Turbine. Right? Kalpakam, split atom. What you get? Your electricity?
Split atom, boil water,
That's all. Split atom, get the splinters, neutrons, high kinetic energy, stop them using moderators that gets heated up, exchange the heat to with water, and then do what? And then what do you get from the water? Steam, and run a turbine, and there you have something rotating with reference to something else. There is a coil, stationary, and a magnet rotating, or the other way. Then you get, that is how everything is come. Direct conversion using solar energy and all that, wind energy are very, 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 very small. They are becoming bigger, but still long way to go. Okay, fuel cells, all those things, chemical energy. So now, therefore, you should realize a very simple concept over the period of time. Can you see this? What is that? I have connected to the 2 ends of the coil LEDs. one I connect in one direction, the other one I connect in the other direction. So this LED will go when the current is in one direction, this LED will go if it is in the opposite direction. Now I do. That means what? Can you see? So people have done battery out of this, torchlight out of this. You do like that, each pulse you charge to a battery and then use it to go for outside when it is dark. You can use it as a battery without any battery. I don't know whether you see the point. You can use this to charge and then use it whenever you want. Okay, without any electrical mains power or something. Okay. So now what happened in this case? When I put magnet through copper tube, this is copper tube for you. For me, it is a coil of wire continuously wound without insulation. Correct? Yes, so it's a solenoid. I can effectively imagine that it's a solenoid. So I push magnet. So what happened? EMF. That is what Faraday law says. Laws of electromagnetic induction. Okay. So this voltage will be millivolts. But what is the resistance of this copper? Microohms, milliohms. So millivolts divided by milliohms. What is the current? Milli. Don't say like that. Amperes. Milli, don't say milli. It will be amperes. So very large current can flow through this. What is the effect of that induced current by Lenz's law? To oppose the change causing it. I don't know whether you realize. Electromagnetic, laws of electromagnetic induction. There will be an induced EMF, that is Faraday's law. And the effect of the induced EMF is to generate a current which will produce a magnetic field to oppose the change that is causing that induced EMF. Right? So when the magnet goes in, it produces a voltage. That voltage will generate a current through the copper. And the current will generate a magnetic field to oppose the motion of the magnet. That is causing the effect, right? So that means it will provide an opposing force to a gravitational force down, which is constant. This opposing force depends on what? The EMF. The EMF depends on what? d phi by dt. What is d phi by dt? Rate of change of flux. You have studied or not? All of you. So, therefore, as the velocity of the magnet increases as it coming down the gravity, the induced EMF will be more, current will be more, opposing force will be more. At some stage, what will happen? Both the forces, this is a small magnet inside the tube. There is a opposing force due to the induced current, due to Faraday's law. There is a downward force which is constant, mg. So at some stage what will happen? This magnetic force will become equal to mg. Then what will happen to the magnet? Stop. It will get suspended, right? No. Newton will perform somersault in the grave if you say that. Because you know what is Newton's first law? What is Newton's first law? Every body continues in its state of rest or of uniform motion. What is that uniform motion? Uniform motion is a motion you achieve when all other forces are zero. So at this stage, this force is equal to this force, but you did not achieve it here when you dropped it. It is here at some distance by which it has gained some velocity. So when they balance, it will still have some velocity, and that will be the terminal velocity which it will come down and you can catch at the bottom. Okay? So, therefore, this is the principle of the terminal velocity. You would have done something, Stokes' law you have done, 6 pi a eta v. That is again a force proportional to velocity. Here is an electromagnetic force proportional to velocity. Wherever you have got, you will get that. Somebody jumps from the aeroplane. No mind. Somebody jumps from the aeroplane, what happens? He will spread the parachute. When he spreads the parachute, what happens? Viscous forces will come into play. That is again proportional to velocity. Gravity increasing the speed. This force increases. At some stage, these two will balance, like here. Then what will happen? The fellow will land with a terminal velocity without any harm on the ground. Right? Rainwater. We never even imagine. Rainwater, what is the thing? Around 2 kilo. from the ground, 2 kilometer. What is velocity? I don't have to derive for you. What is the velocity with which your body will reach the ground from some height? Root of 2gh. I say 2, g is about 10 approximately, h is 2000, 2 kilometers. How much is that? 200? Otherwise, mark will be deducted here. You have to say 200 meter per second. That is equal to how many kilometers per hour? Oh, I don't know. 5 by 18, 18 by 5, something I will have to do. Then what happens? 720 kilometer per hour is the velocity with which raindrops will come and hit the ground. If there is no air. If that is the velocity with which aeroplane will fly in level far away, for 40,000 feet. If it comes and hits on us, no human being, no plant, nothing can be there on the ground. How wonderful, yeah. The whole thing is adjusted for you to live peacefully all the time. Still we keep complaining, right? So, therefore what is happening? It has already reached the terminal velocity even while falling by small distance. Therefore, you go and dance in the rain, nothing happens to you. Right? Good. Now, in the same line, this is a very nice experiment. What I have here? Here again I have a coil and I have a stem, metal stem, MS. So, I connect it now to AC. AC means what? Alternating means what? Sine wave, okay? Like a sine wave. You also should remember this means one, you know the 3 pins. What are those 3 pins? One is called phase. I don't know whether you heard that term. One is called the phase, the other is called neutral. The third one is called ground. Ground is ground. Everybody knows. Actually, the third pin, the top third pin will be directly connected to a copper, thick copper wire. It will go to the ground with a big pole where it is a bit moist to quickly ground all the electrical short circuit. Okay. But these two are the important things, the bottom. One is called a phase, the other is called a neutral. Neutral means I don't join any side. That one, this is phase means what? The voltage in this wire will go high, go low, go high, go low, sinusoidal. This is not. Only one wire will go up and down. When it goes high, this becomes positive, this becomes magnetic, current will go like this. When it goes level, current will go from ground to the neutral to the other one. Do you understand what I am saying? So you should recognize all those things. So it is an AC, and now I have connected to this. And I have a small switch here, which is a push to on switch. When I push, current will flow. So I have aluminum washer. I am going to put it on top. Then I press momentarily. Oh, jumping. Can you see that? So what is this experiment called? Jumping ring. Once more. Now I have one more. What is this? Again the same washer, but I have cut radially. Can you see that? There is a cut here. So I am putting this in place of the other one. Huh? I don't know. That's what you already given the answer. Okay. So this is not jumping, this is jumping. Correct? But you have to first tell me why it is jumping. Then we can see why it is not jumping.
That one is jumping because it's connected completely, circuit is complete.
Where is the circuit? There no power.
Connected totally.
How? I have not connected to any battery, nothing.
That one, the current cannot completely go through the entire.
No, here it is completely flowing and going back.
But there's a small little several traces, so hence that's why.
Okay. Well, yeah, it's a good answer coming close to that, but still it is not complete. But anyway, this is AC. When a current flows through a coil, what will happen? Just now we saw. When current flows through a coil, what will happen? Magnetic field is induced. But it is going up and down. So what will happen? Magnetic field also oscillating. Correct? So when the magnetic field is operating and the conductor is stationary, what will happen to this? There will be induced current. EMF, electromagnetic induction. Just now I told you, due to the turbine, you can make the magnet rotate, coil stationary, make the coil rotate, magnet stationary. If there is a relative motion, there will be a liquid nitrogen முடியுமா? காமிக்கலாமா? முடிஞ்சா? So when there is a
Already it is jumping out of it.
it doesn't matter. So கொஞ்சமா கொடுங்களேன். A little bit அந்த கப்லே கூட போட்டா கூட அதில் வச்சா கூட. So now what is happening? I hope you understand what I am trying to say. So there is a alternating magnetic field and there is a conductor in its atmosphere. So what will happen? There will be an induced EMF. That induced EMF is also AC. So what is the effect of the induced EMF by Lenz's law? To oppose. So this fellow wants to oppose this fellow. Who is weak, who is strong? You all know it. This fellow is very strong, he is thrown off. Correct? So he is thrown off. That's how it is. But in this case, what is happening? In this case, what is happening? Because it is cut. The eddy currents, this is what we call eddy currents. Small circular currents. Thank you, sir. Small circular currents. Now I am going to do this. I am going to cool this. Now you see here. Quickly observe. See how much it is jumping. Almost just above this, right? Now what I am going to do, I am going to cool it in liquid nitrogen. Luckily we have liquid nitrogen. I don't want to miss that experiment for you. I am putting it in liquid nitrogen. It is boiling, that white fume. Right? Okay, now what is going to happen? Let us see. Let us wait for some time. See, now I am going to put it here. What will happen? What happened? If you cool sufficiently, it will come up to this. Normally, I ask that as a question and show that anyway, it doesn't matter. Tell me, what is the difference with this?
Is it something to do with superconductors?
No, it's not superconductor. Yeah. If that becomes superconductor, I will get Nobel Prize. I can share with you. Room temperature. Okay. Now tell me what is happening.
So the temperature actually decreases the resistivity of the current that is there.
Very good. Clap. Good. So, what is resistance? What is resistance, man? Opposition to current. Everybody knows. In a normal crystal or a metal, atoms are there in the lattice. Electrons, they disown. Huh? No, no?
You can do it once more.
Once more. Can you see? It is definitely much above compared to the previous one. Okay. So, in that normal temperature, what will the atoms be doing? I told you already. They will be dancing. So, if I keep on cooling, what will happen? The dance will become, the amplitude will become less and less. It is almost. Then, what happens to the electrons flowing? Which will be easier for the electrons to flow when they are dancing and when they are not dancing? When they are not dancing, resistance is less to the flow. So, more current can flow. Right? So, therefore, more current flows for the same induced EMF. And therefore, more magnetic field by Lenz's law to oppose. So, it is going very high. Very nice experiment relating the resistance to temperature. The same thing when you, as he said, if you go still lower, in certain metals, it happens what? It is not linearly decreasing. Even when it is above some temperature, below, above absolute zero, it suddenly becomes zero. That is superconducting. Okay? Superconductivity means resistance disappears completely at some temperature. That temperature is called superconductivity transition temperature. You will do some experiments also later on, perhaps, I don't know, some of you. In the low temperature, that is all possible. We can do that. Okay, sir.
Yeah.
So, their application of this is here. It is shown. What is that? These are all, see, we have made around 50, 60 small gadgets. Physics DIY kits we have made. Not only this. I have also made, I didn't bring today. Yes, sir.
In that context, we can tell them lithium bearing copper oxide.
What is that?
Lithium
Barium carbon. Yeah.
So is also here.
Good, sir. Okay. So, you want to say that? Go ahead. Please. No. It is from the horse's mouth. Come.
The superconductivity is the normal people observed really around
But-
2 Kelvin, 3 Kelvin, 4 Kelvin on that range. But in around 1980, 1985, 88, around that time, people have found out that the insulators becoming superconducting. Lithium, barium, copper oxide, why we to 1 to 3
1, 2, 3 compound.
You can actually Google it, the coil is there. So if you cool that to 80 Kelvin, it becomes superconducting.
80 Kelvin means what? Above liquid nitrogen.
Yeah, that's the same temperature.
2 degree Kelvin, 3 degree Kelvin, when first time Kamerlingh on us, when we found superconductivity, it was at very low temperature. He took it by air flight to show people in the academy. Okay, so you can imagine how people have done crazy things to prove their point. You know what Sir C.V. Raman did when he got his Raman effect? Huh? That is booking. Before booking, he has to publish, no? You know what he did? By Morse code, he sent to the Royal Society the entire paper. Urgent. It should go before somebody else does. What do you mean, yeah? If you let us go by ship for 3 months and go and say, I got this matter, somebody in Europe would have done it. In India, already we are all handicapped. The Gedanken experiment only, mostly, right? So, therefore, that genius could recognize the importance of that. And then he sent it by wire, the entire paper. Of course, nobody looked at it. They put it in the dustbin first time. Afterwards, somebody said, no, there seems to be some interesting thing. Let's take out. And then finally they, wonderful. Always that happens. Einstein, it happened. You know that. Right? For everybody, it happens. So, if somebody says your work is useless, you should always wonder, maybe mine is phenomenal. That's why they are not able to see it. So, you should start still working towards that. The conviction is the most important part of scientific discovery. Serendipity comes when you have conviction. Strong belief in what you think, what you do, and then things will happen accordingly. Okay, anyway, so in the 1, 2, 3 compound became so famous because they were all trying with all kinds of conducting material. Metals, this, that, liquid metal, all kinds of things. So finally somebody did something which is a ceramic, insulator, complete. 1, 2, 3 compound, yttrium, barium, copper oxide. Oxide means it is insulator, right? And he was able to show conductivity at 90 degree, 85 degree, etc. Kelvin.
Similar for lanthanide also.
There are plenty now. We have a lot of things and people were trying to see whether we can bring it above room temperature. When you bring above room temperature, what will happen? You don't have to pay electricity charges.
One point that
Please, sir.
it's not that in India we are not working in that area.
Yeah, we
There
have.
are scientists who have been working in those compounds. But the idea of measuring the resistivity did not occur to them. The Nobel Prize would have come to India.
I will tell you one typical example.
Even here in IIT Madras,
I know.
physics department also they are working in that material.
Subbarao, right.
So you have to think sometimes out of the box.
See, I'll tell you, a wonderful prompt he has given. One of our own scientists, well-known scientists, many of you know C.N.R. Rao, right? Professor C.N.R. Rao is a great scientist, Bharat Ratna. He was director of Indian Institute of Science and all that. You go and check his profile. Phenomenal. He has been here several times. Okay? Chemistry, belongs to chemistry. They have published on a oxide. They found it is coming down. They came up to nitrogen temperature, but the transition is slightly below. And their lab in the whole of India, their lab has called helium plant. That means they can go to helium temperature. Helium temperature is at around 2.4 degree Kelvin. Okay, 2.4. He has to come down little bit. You would have been Nobel laureate. Somehow it didn't happen, or somehow he was busy and the students were not thinking in that line. When I went to an international conference in UK, the gentleman flashed his paper, C.N.R. Rao paper. He said, see, they have done the same material, what these people have achieved. But the only mistake they did is, they just did not take it to helium temperature. If they would have done a couple of years before what Bernard Muller, everybody did. So therefore, that's what he is telling to. So sometimes You should try to be completely independent, think completely out of the box. Yes.
Sir, I can't understand why you're taking it to helium temperature, sir.
Huh?
Why are you taking it to helium temperature?
So that's a lot of theory in it, experiment in it, okay? So it has to have certain conditions, it has to serve to become superconductivity, right? So it has to form something like a Cooper pair. Electrons should have some pairing, and that enables movement of the electron without any resistance.
Oh, so they link the electrons linked together.
Yes, yes.
And electrons.
They are called Cooper pairs.
Okay.
Okay?
But is still an open question.
There are a lot of things.
Open question. In alloys and metals, alloys, there is called something called BCS theory that explains very well. But in oxides,
Still we are not able to understand what it is.
theory is still open.
Open.
Some of you can actually.
If you are taking up chemistry or physics and then investigate, it is a Nobel Prize winning problem for you to attack. Okay? Don't look blank here. Only one among you will come. It depends.
Why
Okay?
not all of them?
Why not? Why not all of? But all of them let not do only on superconductivity. Do on several things. Okay? There are so many problems waiting to be attacked. Okay, anyway. Good. So now we are showing an application. Sorry. We are showing application of Faraday's law. What is that? I have a disc. Now if I switch on, I have connected it to a motor. Can you see that? If I switch on, what will happen? I hope it will. Okay, we have to switch on. Is that? Oh, I switched off. Now you see, can you see that disc rotating? Disc is rotating. Here, you know what I have? Say a magnet. I have a small cavity. So I'm going to take the magnet close to this. See what happens as I take it closer and closer to the aluminum disc. Can you see what has happened? Take it out. Can you see? Take it closer. Can you see that? What is this called? Electromagnetic braking. That's all. Electromagnetic braking application. Without coming into contact, normally brakes will do what? There will be a shoe which will come and press the rim of the wheel, and there is friction. Therefore, what will happen? After 3 months, you have to change the brush, the bush, and then go to the auto shop, etc. Here, without non-contact, only through magnetic field, you are able to slow down. Okay? That's all, sir. This is very simple.
Very simple one, but it's not big.
Yeah. Thank you, sir. How much time I have? Okay. So, normally we have material for about 3 hours. But in the timetable I saw it is only 1 hour. 9 to 10, I don't know, by mistake. But when Mangal Sundar told me, professor told me, you have to take for 2 hours. So I am assuming I am taking 2 hours. I hope you are okay with that. Right? So now what? Here what I have, this is a very, very elementary thing. Everybody, I don't know whether I can give a chocolate to anybody who gives the right answer, because it's so simple. You have a PVC tube, I have a wooden block, and I have another stick. So, who has come, not come? One of you come. Anyone? Come here. It's only interaction. Hold it here. Hold it in your hand like this. Without hitting your hand, hit it on that. Be careful, don't hit your hand. What happens to the block? What is happening to the block? Reverse. Hit. Oh. Left and right. Can you see that? Can you see that? The block keeps moving. Why? Inertia. Exactly. You have to recognize properly. When you hit, only the tube gets a stress, force, and it moves. The block wants to remain stationary, so it stays in the same place. Okay. Now there is a filament. So now this is almost the last experiment, right?
If you want it to be last, I have one.
No, I think it's okay. Huh?
I have some more.
More. Okay. So more experiment, I'll tell you how to get more experiment from me. I have something in my hand. Can you identify what it is? 100% everybody will say LED and it's all wrong answer. It is a neon lamp. It's a neon lamp. You would have seen big signboards and all that. That's all neon. You have a neon and you apply a voltage, it will excited. So it will be ionized and so that will be, it will produce a lot of sound, light, beautiful light, different color lights you can do. Okay, so this is neon lamp. That means there is a bulb with 2 electrodes inside. So you have a this is for evacuating and introducing neon at the top. Okay, glass blowing the bulb. They have done it. So here there is neon. Now, if I take this and connect it to a battery, large battery, DC battery, and keep on increasing, at one stage I get glow. What is happening at that stage?
After the thing excited.
Yes, I measured what is that voltage. You know what I got? 70 volts. The lab. In my lab power supply I connected, kept on increasing. When it came to 70 volts, what is happening? What is the voltage between these 2 electrodes? 70 volts. What is the distance between them? About 0.1 millimeter, not 1 meter, 0.01, very small, 0.1 millimeter, something like that. 1 millimeter, maybe 1 millimeter. So what is happening now? What is the voltage? What is the field, the electric field? Electric field is voltage by distance, you all know that. The distance is very small, voltage is 70 volts, but it is 0.001 means 70 by 0.001 will be 70,000 volt per meter. So it's a very large voltage field, it's a large electric field. Because it is a large electric field, it can easily ionize neon. And electrons and ions are separating out. Electrons go towards positive, neons go towards, neon ions go towards. So what is happening because of that? There is a discharge, you get light in all directions. Okay? But luckily, when I was traveling, I found a magic box. So that magic box can make it glow even without all those things. I don't know whether you see that. Can you see that? 100 rupees here. Sure. You can see. Can you see? Can you see it is glowing? All of you? If you are not able to see, can you switch off these lights? One more, sir. Good, thank you. See what is happening? Nothing is happening. Oh, you can see here. I didn't bring ya. I have such a big item. If I go like that, it will be glowing like this. I can take a 4 feet tube light, hold it like that, it will be glowing in my hand. Magically, right? Okay. இதற்கா இது என்னது அது இன்னும் கொஞ்சம் ஈஸியாக தெரியும்னு நினைக்கிறேன். Good. Electricity. Now I think somebody should give me Nobel Prize. I'm able to, energy, you are able to transfer energy in my hand. Right? Something great.
So there's some sort of.
But I must show you what is inside. Correct? அது அந்த switch off பண்ணிருக்கோம், switch off பண்ணிருக்கோம். அப்பதான் இது பார்க்கணும். ஆமா. கொஞ்ச நேரத்துக்கு. Oh, beautiful. Oh, what is this? Plasma lamp. This is called plasma. What is plasma? What is plasma? Fourth state of matter. Fourth state of matter, solid. When you heat it, it becomes liquid. When you heat it, it becomes gas. When you heat it, it becomes plasma. Plasma is ionized state, but overall neutral. Okay? So, this what is inside is plasma. Now you can see the lamp glowing. Not only that, we can make series connection. He will hold one side. இந்த பக்கம் வந்துருங்க, இங்க வாங்க. He will hold the other terminal, I will hold one terminal, we can make it glow. If your hands touch, it is short circuited. Can you see that? It will work for you, it will work for me, everybody, yeah? Okay. So this is plasma lamp for general public to buy from the shop. It is plasma light to buy. But what it is, really what it is Tesla coil. That's what it is. Come. If you get shocked, don't blame me. No, not all of us. Don't touch each other, yeah. Don't touch each other. Short circuiting. Wait. He doesn't have any electricity. No. Both of you are disqualified. Can you come? Hold on this side. Come. Everybody should see. You have to come. Don't touch my hand. My hand should not be touched. See, she has got electricity. So I can eliminate most of the group in this. Okay? It works. Hey, it will work for you later. Don't worry. Okay, now mind.
But something else to show you.
Most important thing is, what is the most important thing here? This is a Tesla coil. Nikola Tesla was a contemporary of Thomas Alva Edison. Who is Thomas Alva Edison? The biggest scientist. When he died, somebody said, when somebody invented, he's a great inventor, but he overlooked a few, like television and all that. That's what he said. And when he died, Thomas Alva Edison, the entire US switched off lights for 2 minutes. They didn't stand in silence. They switched off light throughout US for 2 minutes in honor of the great guy. I went to his lab and sat in the same chair. Anyway, where Thomas Edison used to sit there. And then, when Thomas Edison was there was another guy. Who is that? Tesla. And Thomas Edison said, we are now able to generate electricity. So I can now make entire US bright. I will send everything DC. Tesla said, my dear Thomas, you have to send by AC. Now you know what it is, AC. So even Thomas Alva Edison can give a wrong answer. You understand? So who gave the right answer? Tesla. You know why? Why AC? Crazy, yeah? I tell you. If I tell you what all we do to get electricity to your homes, it looks crazy. You know what we do? You generate a voltage only at 300, 400. You know what we do? We change it to 44,000, 22,000 volts. And then what you do? You send it wires to several kilometers. Then what you do? Put one more big transformer near your flat. Bring it to 440, 220, give it to your house. And you do what? Reduce it by using transformer and all that. Make it 6 volts and make your cell phone charge. Most of the appliances in the house, except fan, light, etc., you require only 6 volts, 12 volts, something like that. So, crazy things we are doing. Correct? How do you justify this?
Innovation.
Huh?
Like, sir, we say we do crazy things that we can innovate and create.
Not innovation. Just like you want to innovate, so make it 20,000 volts. It's not like that. Voltage into current is a constant that is called what? What? What only? It's only what? Okay. So, voltage into current is what? Energy. Right? If I now increase volt, keep the watt same. If I increase the volt, what should happen to current? Should decrease. If I send through copper wire from here to 100 kilometer away town, what is the resistance of copper? We never recognized. resistance of copper is 10 power minus 5 per meter, ohms per meter. But what is the distance? If I send it through 10 power 5 meters, then what will happen? 1 ohm. You understand what I am saying?
Yes.
So if you send by kilometers, then what will happen? The resistance becomes significant. So when I send a current, I square R is what? Joule's heat. Joule's heat, you have studied, no? Current into resistance square, IR square. So there you get heat, and therefore that is I square R, sorry. IR square this side, no? I square R, good. So that is heat energy, that is loss of energy. So if you want to transfer energy from one place to another with least loss, you have to increase the voltage, reduce the current to very low level so that even through long distances the loss is minimal. Therefore, you are ready to again step up here, step down here, still it is economically viable rather than sending the whole thing as such. Therefore, Tesla is great in that. That's why we are all having in every flat you have a transformer nowadays, right? Etc. Okay. Now the other one, this is a very interesting gadget. If I switch on, what do you get here? Nice sine wave, right? But how a sine wave is produced? All by cooperation. Now tell me what do you see? What do you see? Yeah, one single particle going up and down in its own equilibrium position, about its own equilibrium position, right? This is vibration, simple harmonic motion, whatever you want to call it, right? Now what I do? I remove this, take another one which has got 3 slits. Now you find phase difference. You can see the 3 are vibrating, but there is can you see that? Everybody can see that. So they are all cooperatively working. Now I remove it, I put the whole thing here. Now see, that is what sine wave is all about. Wave motion is nothing but, so if I put a small thermocol ball on the surface of a pond, somewhere in the middle, I put a stone here, that will not vibrate. Only when the wave goes there, it will vibrate. And it will, how it will vibrate? It will not go like this. It will just go up and come down. Next wave comes, go up and come down. Each one is doing their job. But there is a slight delay, which we call phase difference, between the neighboring fellows, and all of them combine together to form a waveform. That is what is moving. So the disturbance is moving, not the particles in the medium. Okay? That's how sound travels, so many things are traveling. That is what we want to show you. So now, now what is happening is, to 40, 50 years I have been doing this kind of thing several places, right? So then what I thought, let me perhaps start someplace. So I started in Adyar, I told you already, what is the name of that? Falling Apple. What you have to do there? Anybody can walk in. Above the age of 10. 8 also are there. 8, 9 years also there. When they come, what I do? I don't do anything. I ask them to do. I give them whatever they want. They will do things on their own with their hands. I will provide them mentoring, some support. And they will do without even knowing that it is science they can do. Pure fun. No exam. No exam here. How wonderful. No comparison. You look at that fellow is able to do, you are not nothing. This fellow will do at his own pace. This fellow at his own pace. That's how the whole thing, education should be there. Each one is good in certain things. So you should groom them in that particular skill. Okay? So, no comparison, no this thing. And then at your own pace and at your own time. It is open all after school hours. I'm not propagating it. Don't think like that. But I'm sharing the concept. What is the idea behind it? We are all chasing marks instead of chasing knowledge. How do we do that? Therefore, I have a center where this is what I want people to do. Pure knowledge. You come. I have electronics kit. I didn't bring it to you to show you. With which 40 simple experiments, all will glowing bulbs. semiconductor, diode, transistor, this, that, etc. Everything. You can go to Arduino, you can go to robotics, everything you can go. But you have to go it in small steps. So this is something that I am doing there, and part of that only I got lot of simple experiments which are DIY. So what is my logic? My logic is not to giving such lectures. Unfortunately, I am telling at the end, right? I should have told this at the beginning, because I want you to do. There is a difference. You can always say, look at that fellow, Kohli, he should have hit it to the 6, yeah. Then he said, you should take him out. They will all say from the gallery. When you get them into the field, what will happen, you know. You follow, and it's always easy to criticize others. When you do it yourself, you will really learn by making errors. So for me, making errors is most important. That is why people say failures are stepping stone to success, because every failure wants to teach you a lesson. If you don't learn that lesson, no use of that failure. But along with that, therefore I tell my students, please make mistakes. Okay? Don't tell your teacher, yeah. And then, but I tell two corollaries. One corollary is what? Please don't try to make all mistakes yourself, yeah. Give chance to your friends and learn from that. Next one, please don't repeat the mistake. When you repeat the mistake, what it means? You have not learned the lesson. Right? Keep making mistakes. Learn from them. You will all be great. So I am wonderfully interacting with you. Okay? I am so thankful to Dr. Mangal Sundar and the whole team for putting together such bright young kids from various schools around, and I hope I have shared some experience with you all to make science learning exciting by doing things on your own. That's the whole concept. Okay? Thank you for your attention.
Swayam Prabha. Digital India. Educated India.